Welcome, multivariable calculus friends. I hope everything's going well. We are in the midst of wrapping up chapter 15 and starting our review of integration. So in a way, we've kind of wrapping up the calculus 3 topics, but we're going back to finish strong on integration. So the beginning of this, I've just got some examples here to kind of jog your memory on the details matter. A lot of these were challenging problems last year in BC, so I want to make sure that we're all good to go for going in the future. I'm also going to be assigning some homework problems to you in your book. I showed you in the course navigation, remember in the in the course syllabus, right? There's that link to the textbook, and then I'll if it's a odd answer, the answers are all solution guide worked out for you. So make sure that you're doing that. So today I'm going to call this section 8.1 in your textbook. Seems like the light is a little bright. Let me see if I can cut it back a little bit. Oh, we'll try. I'll keep an eye on the monitor because it seems a little washed out today. I think two of this might be too dark. Maybe I'll go on this here. Yeah, let's try this. That's actually even better, isn't it? Okay, let's try that. Okay, I'll keep an eye on the light, but you've got that. So review of integration is what we're starting the chapter here. Some topics to look forward to, and I will have some packets with review problems attached. Integration by parts was a big one. All those trig powers where you have to do some substitution, improper integrals. So those will be on the horizon, but just kind of a review idea here in 8.1 in your textbook. So 3 examples, and it's one of those, if you remember, I like these problems that look the same, but really are they? Examples. Example A, the integral. Still not real happy with the way the light is today. It's really strange because I've been doing this setup all along here. 4 over x squared plus 9. Okay. And you might think, oh wait, that's probably u substitution with u being x squared, but then if we did that, it'd be 2x on the top, not a 4, so that won't work. Any other ideas? Oh yeah, all those inverse trig ideas, right? So this 4 could come out. We could say 4 times integral of 1 x squared plus 9 dx. And this looks like u equals x, du equals dx, a equals 3, and that reminds us of 4 times the integral of 1 over x squared plus 9 is going to be the antiderivative then, is going to be 1 over a, 1/3, arc tan u over a, x over 3, plus c. So we'd end up with 4/3 arc tan, or inverse tan x over 3 plus c. All right? Another similar one, but not exactly the same, so details matter. 4x over x squared plus 9 dx. 4x over x squared plus 9. This one makes us remember, oh yeah, if u is x squared plus 9, the whole bottom there, our denominator is u, du would be 2x dx. A lot of you are saying, well, I could split that 4x into 2 times 2x, so 2 times 2x over x squared plus 9 dx. Sure enough, that's my d over u, right? So I've got 2 times the natural log, absolute value of x squared plus 9 plus c. Okay, do we need the absolute value because the argument is going to always be positive? No, but it's not going to be wrong if you had it, so that's always the best answer there. Okay, and another example in this, are they similar? Well, they're similar, but not exactly the same. 4x squared over x squared plus 9 dx. This one is one that we seem to forget because we forget to, if the degree is the same, the first thing we need to do is do some division here. So let's do a little bit of division. X squared plus 9 is going to go into 4x squared. So what do I need to multiply that x squared to make it a 4x squared? Times 4. 4 times x squared is 4x squared, right? Plus 4 times 9, 36. Draw the line and change the signs. 4x squared minus 4x squared, that's 0, minus 3x, 36. So my new integral now is 4, right? My answer, and then the remainder, minus 36 over x squared plus 9 dx. Okay? So questions there. That's kind of rhetorical. Hopefully you're good to go with that. So I've got the antiderivative of 4, which is going to be 4x. And then I've got the antiderivative, well, that looks like a lot like arctan. We've got u over a. We already did that one, right? So it would be minus 36 over 3, because that's the 1 over a, arctan u over a. So u was x, a was 3, plus c. So 4x minus 12 arctan x over 3 plus c. Okay? In page 520 in your textbook, okay, there are a ton of integration rules, and it makes more sense because up to this point last year we hadn't talked about some of the more advanced topics. So chapter 8 is what I would call advanced topics in Can You Integrate. So on page 420 in your or 520, sorry, in your textbook, there's a list to this point. If you don't know these, I would make that a goal until you know them on flashcards, okay? And don't just say and look at them and say, yeah, I know these, but recite them back to your dog, cat, social distancing friends. You can text each other, I'm not sure. But make sure you know these cold, all right? So that's one thing I'd like to do. Then the next thing I'd like to talk about, and they do a good job in your textbook, so if you want to refer to that too, what they call tips on matching the integrand. To those 20 rules that we knew to that point. You know more than 20 rules by now, but matching up to that point, and we'll kind of just run through these. Expand the numerator. So I'll give you an example. If your integrand is this, x squared plus 1, quantity squared, right? You can't just say u substitution because you can't say u is x squared plus 1 because I've got u squared. You don't have any of the du there. So you can't just assume that everything's going to be u substitution. So you'd have to expand that out. X to the 4th plus 2x squared plus 1. And you know how to do that. Okay? Number 2. Separate the numerator. So an example might be 1 plus x all over x squared plus 1. Looking at that denominator, from one perspective it might be an arctan kind of thing, but from another perspective with that x, it might just be a log kind of thing. So you might be able to do 1 over x squared plus 1 plus x over x squared plus 1. And do those integrals, each piece. All right? Another idea, complete the square. Especially with denominators. Let me show you what I mean by that. 1 over 2, well, I'm sorry, 1 over square root of 2x minus x squared. Well, I can't just say u substitution, right, and say it's u to the 1/2 power on the bottom or u to the negative 1/2 power if we move it up to try to use the power rule. Because I don't have any x and 2 and minus 2x, and there's nothing up top, so that won't work. You should be able to do that. I'm going to rewrite this as the square root of, save some room, right? Factor out a minus sign and put these in order. Minus x squared minus 2x. Save some room. 1/2 the middle term. So x squared minus 2x. I factored out a minus sign to reorder those, to put them back in better order. But if I add 1, right, that would complete that square, because -2, half of that is -1, -1 squared is 1. But I didn't really add 1 inside the square root. I subtracted because that minus sign, if I redistribute that minus sign, so that 1 minus 1 would end up with 1 over square root of 1 minus what? X minus 1 squared. And that looks like arc sine to me. Okay, so practice those. Topic number 4, divide any improper rational function. In other words, when the degree was the same or higher on top. Improper rational fraction there. Function, but rational fraction there. Rational function. So that's kind of like the example we just did on the front of the page, 4x squared over x squared plus 9. You have to divide because the degrees are the same. So it's like that one. Okay? So we'll use that as an example. Number 5, add or subtract the terms in the numerator. So an example of that might be 2x over x squared plus 2x plus 1. Okay? And again, we're just working with the integrand. We're not doing the integral. We're just working with the function. We're trying to take the integral out, the integrand. If I wanted to try u, I could say for the bottom, it'd be u equals x squared plus 2x plus 1. So du would be 2x plus 2. Well, I've got the 2x, but I don't have a plus 2, do I? So I could say, well, that's equal to 2x over x squared plus 2x plus 1. And then if I wanted to, I'm going to do it in a different color. Let's see if this shows up with this color. I'm not sure it will, but we'll do it in red to see if it shines a little brighter here. If I wanted to add plus 2 to that, right? So it's a little different. I could later say plus x squared plus 2x plus 1, and then say minus 2. So this plus 2 minus 2 offset each other, but this one helps us do the log integral here. What might you do here? Well, if we were able to factor that, maybe we could think about an arctan kind of idea there, or some other way to break that up. So think about that. Okay. You could also use u substitution maybe. So maybe not arctan, but u substitution. But an example there where you had to break it up by adding or subtracting terms in the numerator. Trig identities. And that might be as simple as converting everything to sine and cosines, right? And seeing what you get. It also might be something like remembering sine squared x plus cosine squared x equals 1. Because a lot of times you'll have one of the other that you don't want, and you need to convert them to the sines or the cosines. But if you've forgotten the others, the other Pythagorean identities, if I divide everything by sine squared divided by sine squared is 1, okay? Cosine squared divided by sine squared is what? Plus tangent squared. And what's 1 over sine? Well, 1 over sine is going to be what? No, cosine is not. That's not. I misspoke, didn't I? 1 plus cotangent squared x equals 1 over, that would be cosecant x. So here I'm dividing everything, we'll just say 1 over sine squared. So if you forget those, and I oftentimes forget them, just There it is, right? So divide everything by sine. This time we'll divide everything by cosine. So cosine, sine divided by cosine is tangent. That one we know. So tangent squared. Cosine divided by cosine is plus 1. So cosine divided by cosine squared over cosine squared is 1. And 1 over cosine squared, secant squared x. Okay? You've got those. Also, remember sine 2x. That's 2 sine x cosine x. The double angle formula for sine would be one that you'd want to know. Cosine double angle would be one that you want to know. You've got those, okay? And then another idea, and then we'll wrap it up with this one, is multiply or divide by the conjugate. But usually when we multiply, you're doing it 1 over 1, right? So an example might be 1 over 1 plus sine of x. Can't do u substitution there. It's not log of that because you don't have any du to finish that. But if I multiply that by the conjugate, 1 minus sine x over 1 minus sine x, and put some parentheses around this too. What you'd get is 1 minus sine x on the bottom. Okay, cool. But then you'd get what on the top, I mean. If you multiply that out, you'd get 1 minus sine squared of x. 1 minus sine squared of x. Isn't that cosine squared? So 1 minus sine x over cosine squared. And you could do some work there. Now you've got a simple fraction that you can break that fraction up. So separate the numerator. Rule number 2 above would apply here. 1 over cosine squared x and minus sine x over cosine squared x. So that's something we could do. And that's secant squared, so I bet you know the antiderivative of secant squared. Minus sine x over cosine squared x. We could do u substitution there, right? If u equals cosine, du is going to pick up a sine there. So that would work. All right? So I'll assign some problems here.